we just recently did what? We just recently learned how to do a hypothesis test for the population mean when the population standard deviation is known. And throughout the process, right, I suppressed it. You may or may not have, but we were likely both thinking, what the cut the. Just like in Chapter 5, this seems a little bit contradictory, seems perhaps a little bit useless. Why would I be doing a hypothesis test for the population mean if I knew what the population standard deviation is? And you're correct. In reality, we generally do not know what the population standard deviation is, so this is sort of our correction section, sort of taking a step towards something a little bit more realistic, something a little bit more applied. Now, you're going to see that the changes we do for hypothesis testing are really going to parallel the changes that we had to do for confidence intervals. When the population standard deviation is unknown, really, virtually, the spirit of the hypothesis test is sort of unchanged. The only thing we need to do is we now need to replace the unknown population standard deviation with the known sample standard deviation, just like we did for confidence intervals. Doing this, unfortunately, changes the mathematics. It changes the distribution of our test statistic. It no longer follows a z distribution, which is why we were using the normal CDF to calculate probabilities or p-values, but instead it follows, right, that somewhat familiar yet still enigmatic t distribution. So our test statistic formula looks like this, right? It's essentially the same formula, it's just I replaced that sigma with s. It's my test statistic, it follows a t distribution, so I use a t to signify it. And remember we talked about in Chapter 5, every t distribution has associated with the degrees of freedom. And just like before, the degrees of freedom are going to be n minus 1.
So since our test statistic follows not a z distribution in our previous hypothesis tests, but instead a t distribution, we can no longer compute the p-values using a standard normal table, or the probit function, or the p-norm, or whatever it is that we were using. Instead, we have to use a t-table, or some function in SAS and R that will calculate t probabilities. Now, in terms of our table unfortunately can't give us exact p-values the way it's constructed. The way it's constructed, it can only give us bounds on p-values. Although we'll see that, I mean, typically all we care about usually is the p-value more or less than 0.05. So typically knowing bounds is good enough to make a decision. Nonetheless, we will see that SAS, of course, can generate exact p-values quite easily through proc univariate. So when we wrap up this PowerPoint, we'll take a look at an example of that. But before we do that, I want to look at 3 examples of using the t-table. Now this is important. So pause this, get your t-table out, get ready to take a look at it. There will be questions, numerous questions, on future tests. We are going to have to understand how these bounds work. A lot of the test statistics in 512 follow t distributions. When you're taking a test in class and it's a closed computer test, you're going to be using the table to get your p-values, and you're going to have to say it's between this and between that. So you need to understand these examples. If you don't understand the examples, if you don't see where I'm getting these numbers from, then you need to come talk to me or one of our graduate assistants. So here's our first example. Let's say that we're testing whether or not the mean is greater. Right? Remember, we had 3 possibilities for what the alternative can be. This is the situation where we're testing where mu is greater than mu naught. Our sample size is 16, and let's say that our test statistic is 4. So let's go ahead. A sample size of 16 means our degrees of freedom are 15. So we go to the 15 row in our t-table, and we're basically just going across to try to find that test statistic, to find that 4. Now notice the number 4 falls between those last two columns. Falls between those last two columns. It's very, very, very close to the last column, right? So it's between 2.947 and 4.073. So those are percentiles. That's area to the left. But remember, the p-value for a greater than is all the area to the right. So what that basically is saying, it's saying that the p-value is between what would that be? Between 0.5% and 0.5%, or right in decimal form between 0.005 and 0.0005. Again, convince yourself that makes sense before you move on to the next example. Here, we test that the mean is less than our hypothesized mean. Here we expect a negative test statistic. It turns out our test statistic is negative 1.22. Our sample size is 24. So if our sample size is 24, that means we go to the 23 row, and we go across looking for 1.22. So 1.22, that's somewhere between 1.060 and 1.319. Okay? So again, those are percentiles. So, right, area to the left is 85 or 90. It means area to the right is 15 or 10. Now, of course, area to the right, by symmetry, area to the right of these positive numbers is the same as the area to the left of the negative numbers. And so that implies that the p-value is between 0.10 and 0.15. Again, draw some pictures. We're using symmetry a little bit here. If you cannot convince yourself it makes sense, let me know. There's going to be test questions that require you to understand this type of logic. There's going to be test questions that are going to require you to be able to use this table to come up with bounds of p-values. And again, notice those bounds are perfectly fine, right? Because again, typically all we care about is whether the p-value is more than 0.05. So even though we don't know the exact p-value in this example, we would still be able to say that, yeah, at the 0.05 level, we're going to fail to reject the null hypothesis. Previous example, of course, we had strong evidence to reject the null hypothesis. Now let's go ahead and see what our third example looks like. So now we're doing a two-sided test. Mu is not equal to mu naught. A sample size of 25, a test statistic of -2. So a sample size of 25 means that we go to 24. We're looking for 2 to get as close as we can to 2. That's between 0.95 and 0.975. So we would be tempted to say that that area is between 0.05 and 0.025. But remember, since it's two-sided, we take that right tail area, which we know is somewhere between 0.025 and 0.05, and we multiply it by 2. So that means that our p-value is between 0.05 and 0.10, probably looking at this table very close to 0.05, but still probably just a smidge more than it, which again means, even though we don't know the exact p-value, we could still say at the 0.05 significance level we would fail to reject the null hypothesis. Now, as I mentioned, we can do this in SAS. We can do it in SAS through proc univariate. Let's go ahead and take a look at that. Here's proc univariate. It's the serial data set. I did carbohydrates. So this is just standard proc univariate output. All I did was just var carbo. No extra tweaks, no extra syntax. Now look at that sort of middle area where it says, I'm sorry. Look at the bottom area where it says tests for location mu naught equals 0. So what's being done here is that SAS is testing Well, it looks like it's actually testing, well, it's given the right tail area of a test that tests whether or not the mean is equal to 0. The mean carbohydrates of, I guess, presumably the population of all cereals, of which our data set is just a sample of. Our test statistic is 29.93. That's the student's T. So that's basically saying that we're 29.93, almost 30 standard deviations. Our sample mean of 14.6 is almost 30 standard deviations above the hypothesized mean of 0. The p-value associated with that gives us the area just to the right. It's less than 0.0001. So if we were interested in a two-sided test, which we often are, we would multiply that by 2, and that's still going to be less than 0.0002. So a very small p-value indicating that it's highly significant. There's an extreme amount of evidence saying it's different than 0. But that, I mean, that makes sense. I mean, 14 is vastly far from 0. And this test is not probably a very interesting one, right? I mean, probably a lot of cereals have carbs other than 0, and you can't have negative carbs, so of course it's going to be different than 0. It's a bit of a silly test, but this is the default in proc univariate. Now, in a lot of our other examples, we've done things like we've tested whether or not the mean fat content is, say, more than 30, whether or not the mean time to completion is less than 240, whether or not the blood pressure is less than or equal to, is different than, 115. So how can we put some number other than 0 into proc univariate? Well, let's take a look. We can change that hypothesized mean with the mu 0 equals command in the first line of proc univariate. So from that first line, we put mu 0 equals 14. Now our output's going to look a lot different. So our sample mean is 14.6. We see now that it's saying this is a test for location for mu not equal to 14. That t statistic is saying that 14.6 is 1.23 standard deviations above the hypothesized mean of 14. And the area to the right of that is 0.2243. If we were doing a two-sided test, the p-value would be about 0.45. Either way, it's well over 0.05. So we would say at the 0.05 significance level, there is not enough evidence to conclude that the mean carbohydrates of all cereal is different than 14. Easy enough, right?